Welcome to Chapter 19. In Chapter 19, we're switching to topics in numerical analysis, and this material is going to have a very different feel from what we were learning previously in Chapters 7 and 8. Chapter 19 is something of a hodgepodge or a mix of different topics, and I created this slide to help you understand which ones I'm going to be emphasizing in Chapter 19. In 19.1, we'll look at different types of definitions of errors. In 19.2, we're going to look at root finding. You'll remember that in Chapter 8, when we were looking for eigenvalues, we needed to find the roots of a quadratic or a cubic equation. Well, for those kinds of problems, or larger polynomials, or any other equations, we'll often want to find out what are the roots. When you set them equal to zero, do you get zeros? And so finding those roots is something that we'll be looking at a couple different methods. Your book covers more, but I'll cover the fixed point iteration and Newton's method, one of the more powerful methods there. Then we're going to look at interpolation. In 19.3, there's a number of different interpolation methods that are introduced, but I'm going to emphasize the Lagrange method. And then we're going to briefly just skim over 19.4, which is covering splines. And then we're going to look at 19.5, numerical integration and numerical differentiation. I wanted to review the recommended problem sets, again, odd problems from your textbook, where I've covered 19.2, 19.3, and 19.5. Your book doesn't have problems in 19.1 that are close to what I'll be asking for, so I didn't give any from 19.1. And again, 19.4 is on splines, which I'm only giving brief coverage to. So I didn't have any recommended problems from that section either. Let's start off looking at floating point numbers, recognizing that in computers, how we store numbers is very different than how we conceptualize them. And for example, when a number is stored, a real number is stored in a computer as opposed to a whole number. When a real number is stored in a computer, it's actually stored in two components. First, you have in the scientific notation version of things, both a mantissa and an ordinate on the exponent. And typically, in modern computing, we store numbers in binary form. So we'll have a binary number stored with both the mantissa and the exponent component of the scientific notation version of the number. Why it's worth mentioning that is because there are limits then on how we represent numbers. We can only have a limited accuracy in how we represent a real number, and we also have a limit to how big and how small a number could be. That is, and I don't mean small, how negative, how close to zero a number can be. We have limits on that. Because whole numbers are stored as an approximation, we need to be mindful of that. We have to be careful never to check for equality in real numbers, or not expect it to be a reliable check. So if you've got some number that you're going to reduce in increments down to a particular value, you've got to make sure you don't say start reducing this number by equal amounts and when it gets to this number stop. If you are starting at 10 and trying to take the number down to 1 in steps of 0.25, do not check for, and when that gets down to 1.0, stop, because it might get very, very close to 1.0, but not exactly equal to 1.0, never become equal to 1.0, and then just continuing marching down past the number that you had intended it to stop at. So how do we deal with that? The way we deal with that is we don't check for equality in real numbers. We say if the difference between the number that I'm trying to calculate and the number that I want to get to is less than some very small amount, then you should stop. So if the absolute value between the number that you're calculating and the number you want it to get to is less than some tiny little number, then you know you've got close enough to it and you should stop. Round off error. Limited precision, limited accuracy in our ways of representing real numbers will always be present, and will always introduce round off or truncation errors into every calculation that we ever do involving a computer. That's always going to be true. And that's one of the reasons why I would never ask a computer to check for equality. If you did do a check on equality, it could very well or probably fail. So you should check to see if the absolute value of the number you're trying to get and the number you're trying to get it to is less than some very small amount, and use that as your test of equality. Your conventional round-off rules that you learned from high school or earlier will be the ones that I'll expect you to apply, but I strongly encourage you to keep your extra digits till the end of all your calculations and round off only when reporting your results. Very typically, if you have a 5-part problem, you should not think about rounding off in any of the parts of the problem, and only round off when you report the results. So you carry all your digits and do all parts of the problems and report your answers for each of those at the end. Do not use some rounding in the first part of the problem. So if you're working on problem 5A, if you come up with an estimate in 5A and round to a certain number of significant digits, do not use that rounded number when you move to part B. Use additional digits when you move on to the additional parts of the problems. You have to carry the extra digit, otherwise you are not doing the problem accurately. Remember, we always carry one digit more than at least one digit more of where we have certainty in our digits. And then you report only to the number of digits that you're confident of. So okay, that's probably some review for all of you. When we're looking at errors in numerical results, we commonly need to look at how much error is in your result. This is one of the more important things that we do when we're using any numerical approximation method. So what I'd like to do is point out that your textbook and I have a difference of opinion on this, and I think I'm in the majority of how most people would perceive definition of error. And suppose we have some approximate value a tilde and our true answer a. I will usually define error and relative error using equations shown, where I take the approximate value minus the actual value. And your textbook uses the reverse of these, and it would get the opposite sign. So I wanted to use the example of, suppose you were coming up with, you have a true answer of 10, and you come up with an approximation of 9.9. By my definition, you've just undershot it, so you get an error of minus 0.1. Your book would say you have an error of positive 0.1. I find that confusing. I would think that if you heard that you had a error of 0.1, you would think that your approximation must be 10.1. So if I overshoot, then I end up with a positive error by my definition. Your book would give you the opposite. So I prefer my sign definition. Most people who practice in this area also use my sign convention, but one way we can get around this possible confusion is on the next slide. I actually favor absolute error and then be explicit about whether you are just over or just under the actual value. With absolute error, you're taking the absolute value of the previous equations and you get around it. I'm actually a huge fan of absolute relative error, because when you're talking to an audience, it's very helpful to be using relative error because they may not have a sense of how big the property is that you're trying to estimate. And by using absolute relative error, it gives somebody a very clear idea right off the bat what scale or magnitude of error you were looking at.